Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a researcher at the SETI Institute and Chief Scientific Officer at Unistellar. Today, we are going to talk about a moon of Saturn called Mimas, and one of the recent results that was published in Nature by a team led by Valery Lainey. Hello, Valery. How are you?
Hi, Frank. Fine. What about you?
I'm good. Where are you located?
Well, I'm in France, Paris, and at the moment it's starting to get pitch black, so it's a bit late.
Okay. I'm in San Francisco, so here it's the morning and we're starting the day. So Valery is an astronomer at the Observatoire de Paris, in an institute called the Institut de Mécanique Céleste et Calcul d'éphémérides. Wow, I said that
Well
properly
done.
today.
Well done.
No, you see, nobody knew I was French, but now they know. All right. So Valery is known for his research on the study of moons around giant planets. And as I mentioned yesterday, they published a paper in Nature, a very interesting journal, as probably our audience know, on the discovery of an ocean. So, Valery, I'm kind of curious. I mean, I've seen that articles in the news saying that you found an ocean on Mimas. I look at picture of Mimas taken by the Cassini spacecraft, and I don't see any palm tree, any beaches, I don't see any ocean. So what is this ocean on Mimas? What is coming from?
Well, this is a pretty good point. Actually, it doesn't look like it gets an ocean. So, actually, at the beginning of since maybe the first space images, looking at Mimas, nobody believed you would have an ocean. I mean, it would not cross your mind, right? It doesn't look like that. So heavily cratered, right? You have this big Herschel crater, like the Death Star shape thing. So it looks like a very rigid, cold satellite. You might say boring if you have in mind Enceladus and its geyser activity, or Titan with a big, thick atmosphere and these kind of things. Well, it's, I would say, maybe one of the most unlikely places at first glance where you would expect to have liquid water. So yes, I fully agree.
Okay.
It look like having that.
So the ocean is not on the surface; is
No.
beneath the
Yes.
crust. All right.
Yeah.
So it's still a boring moon, but underneath is not that boring.
Absolutely. Yeah.
All right. Cool. So, okay. So you found this ocean. I mean, you did not send a spacecraft over there. I mean, to dig into the surface and find it. So, can you explain to us how did you conclude that we found an ocean underneath the surface of Mimas? What did you do for that?
Well, basically, celestial mechanics, so dynamics. So to make it short, to make it easy to understand, just usually we are using. I mean, the analogy is not from it's not coming from me. So I do not. I'm just quoting an analogy we have generally, like when you have a cooked egg and a fresh egg, and you try to rotate them. So the cooked egg, when you do like that, starts spinning. Well, camera is here, and if you do that with the fresh egg, it will spin, stops, and doing some crazy motion, right? So it basically means by looking at using basically dynamics, you can, and rotation in that case, you can start to infer the internal structure of an object. So that's true for an egg, and that's true for a planet, a satellite. So this is basically what we used.
All right. So you use what we call libration in English?
Yes, true. Actually, there are two things you can do with Mimas, having in mind this motion. You have the rotation motion, the spin, and you have the orbital motion. So the rotation motion actually was studied by Radouat Tejedin, who did this PhD thesis in my team in 2014. And what he found out was that if you look at the rotation of Mimas, Mimas is like most satellites in the solar system. It's showing the same face to its planet, like the moon is showing the same face to the Earth. This is because it spins at the same rate as it revolves around the Earth. That's the same thing for Mimas. It spins at the same rate as it revolves around Saturn. And when you have this kind of motion, of rotation, you have a uniform rotation plus extra oscillations. They are very tiny. But still, with the Cassini data, which was a fantastic mission, we succeeded really at looking at these tiny oscillations. And what was found is that you have among these extra oscillations that we call libration. I fully agree, Franck. Well, one of those is too large in amplitude compared to what we were expecting generally.
Mm-hmm.
And the conclusion we had in 2014 was that the interior of Mimas could be rigid, cold body, as we used to believe, but you should have a very elongated silicate core inside under the icy crust. Solution number two, the surface is slipping at the top of the global ocean, and this oscillation we are seeing is just the motion of the surface, but it's not a rigid rotation. In that case, you have a global ocean. So in 2014, we pointed out these two different interior modeling that were fitting the rotation of Mimas. And if you have that in mind, you could say, okay, we don't know, right? So we could have said, that's a science paper. So you can say, well, that's great, sure. But I mean, you are not really satisfied because, first of all, you haven't demonstrated it's global ocean. It still could be the rigid interior. So you're a bit frustrating on that and you really want to know. And the other thing is that most of the community just bought this silicate core solution. Because after all, Mimas is small, right? It's very small, 400.
Yeah, it's 200 kilometers in diameter, right?
Something like absolutely. That. Yeah, 400 kilometers in diameter. And the silicate core is twice smaller. So if you look at asteroids, which have this kind of size, it can look like potato shaped. It could have any shape. So why not elongated thing? And in that case, the community was really happy with that. And then most of the people discarded the global ocean.
Mm-hmm.
So we wanted to know, okay, we want now to really discriminate between both interior. And this is where celestial mechanics strikes back. You've seen the analogy with the star, right? And
can I interrupt you? We're gonna say hi to our viewers because I really want to spend the time I want you to spend the time on celestial mechanics to understand the ocean. So we have people coming from different places in the world: New Jersey, France. That's probably someone from your family. Maine. People from Germany, Czech Republic, Ahoy, Yaxemash. Someone from the beaches of Mimas, but I think it's a joke, but we will see that. We will check. Congratulations, Valery from Dorian. I don't know. That's also a friend of yours. Germany, Scotland, Georgetown, Normandy. It's not a country, but almost a country. Rio de Janeiro, France again, and Europa, Berlin, etc. So we are talking about the discovery of an ocean beneath the surface of Mimas. And Valery was about to explain to us how he basically managed to demonstrate the existence of this ocean by using celestial mechanics. So go ahead, Valery.
Yeah. So I said that the rotation gives you an information. It could be a very elongated silicate core, or it could be the global ocean thing. So you need to have an extra piece of information. And you really want to do it, right? You really want to find a way to do that. And I'm a dynamicist, so my expertise is there. And I thought that maybe we can look at the feedback of the rotation on the orbit. So basically, you might say if the distribution of mass is different between elongated silicate core or global ocean, maybe you have a feedback on the orbit. So I don't go into details because celestial mechanics is a lot of math eventually, but you can do very quick. When you have this piece of paper and you have the easy equation, the rough equation, and say, okay, let's try to get a rough number. And we found that actually we are looking at a signal. We're looking for a signal that is basically 10 kilometers drift on the orbit over 13 years of Cassini data. So we basically used all the Cassini data for trying to nail down the orbit of Mimas and of 19 moons generally of Saturn, because they are all disturbing each other. And eventually we succeeded in getting a small drift on the orbit that told us, yeah, this is a global ocean. Whatever the size of the interior of the core, it doesn't work. It has to be a global ocean.
So you took how many years Cassini has been in orbit around Saturn?
2004, 13 years. 13.
Okay, 13 years of observation by Cassini spacecraft. You took all the Mimas observation, you estimate the position of Mimas observation to refine the orbit, and you measure basically a small deflection or variation of 10 kilometers. Is that correct?
Yeah,
And
absolutely.
that's using complicated math that you describe in your papers and others, you derive basically that there is an ocean. Okay, so let's say, okay, there is an ocean. So now, how big is this ocean? How young it is? How was it formed? Maybe you can answer in the order you want, but tell us about this ocean. What do we know so far?
So let's just say something very simple, very quickly. We have estimate the amount of liquid water on Mimas to be between 50 and 60% of its volume. So
Okay.
that's major part of Mimas is made of liquid water, right? When you think about the surface, you can say, ah, really? So that's the crazy thing. It's pretty young, and it was pretty clear actually in 2014 when we had the idea that you had this ocean solution. We knew that it had to be young because to melt the ice, you need to have heating. And the heating source in this kind of object that you have to invoke are tidal friction, so tides. And the tides raised by Saturn on Mimas. And celestial mechanics, easy equation for maybe master students, but not that easy in a talk like that. You can demonstrate that if you have heating by tides in Mimas, the eccentricity of Mimas has to decrease pretty quickly. And since the engine for all this friction is coming from the ellipticity of the orbit, you know that the ocean must be young, because if it was older, then the eccentricity should be 0 now, and it's 2%, so it's not 0.
It's a remarkable what we can do with celestial mechanics. I mean, it's you know that because you did your entire career on this, but it's always impressive to me what kind of information we can get from this. We have more people joining us. In fact, first I would like to thank Idani Silva for the super sticker. Thank you very much. We appreciate. So we have more people coming from France. I think the entire country is watching us right now, or at least a significant part of it.
Don't say it's not for me again. Nobody knows I'm
here. We have someone from Montara, California, Wales, UK. If you send me flag, guys, it's great, but I need to come very close to the window to see. That's someone from Pakistan, Germany, Colorado, Netherlands, New York City, and more Berlin. Thank you. We are talking about the recent discovery of an ocean beneath the surface of Mimas. Okay, so we know that we have an ocean. We know it's young. We have an idea how it formed. We at the SETI Institute were very interesting when this paper was published. When I saw that yesterday, basically, I texted you and I said, hey, I really would like to have you on SETI Live to talk about that. And the main reason is because for us, ocean means water, and water means potential place where we have life. So is there anything you can say about the existence of life, potential life in the ocean, in this ocean? Do we have any information, or do we have anything we can do in the future to get more information about the composition of this ocean?
Well, a big question. I would say that at least what we can tell, you have a significant amount of water, and this water is in contact with the silicate core. And actually, one of my co-authors, Gabriel Toby, did some computation, and it turns out that the temperature of the water of the seafloor of Mimas is at the level of few to several tens of degrees, Celsius degrees, not Fahrenheit. So you have to translate. Okay, basically, you can have a bath at the place, and it's okay. So that's the good news. So you may expect to have complex chemistry because you have this warm water in contact with the rocks, which is really super cool. That's the good part. Now I have no idea. I don't think really we know how much time life needs to get developed when you are in a habitable environment. So that's a question. So on that, I would say if you are pessimistic, the half filled glass. So if you're on the pessimistic side, you may say, oh, but the ocean is pretty young. Nowhere within 5 to 25 million years you can form life. Or you can be optimistic and say, okay, maybe it's possible because it's pretty young. Still, something that I like, and I want to have your opinion on that, Franck.
My opinion is that it would be great to be able to look at more details on the surface of Mimas and see, for instance, there is some fractures. So we have some material coming from the ocean coming all the way on the top and do some spectroscopic analysis to see if we see salt, for instance, or signatures of metagenesis that we have seen on Enceladus. It's difficult. I'm not sure Cassini has the data and the resolution to do these kind of things, but I'm pretty sure some people will try that. But I will conclude by saying we should really send another mission in orbit around Saturn, because now we have more reason to do that.
Of course. I fully agree. And one question I'm wondering also, maybe you have the answer. We are not sure about the age of Mimas, and it's possible that Mimas is not, it could be a second or third generation of moons in the Saturn system, because we know that tidal dissipation in Saturn, and you know that I'm a great fan of strong tide in Saturn, but now I think all people agree on that. They are moving the orbits very, very quickly, and so you may have collisions and these kind of things. And so Mimas could be a second or third generation of moons, which means that Mimas could be formed of debris of former moons, probably bigger, which had an ocean for a much longer time. So I'm just wondering, if you have some complex chemistry that was developed in these former moons, would it survive collision, and would you see it in Mimas, allowing it to get the next step for life formation or not?
Yes, so basically what you're saying is that remnant of the past life formed by the first generation of moon in orbit around Saturn may still exist in the ice of Mimas, basically.
Yeah.
Well, you know how we're going to do that? We find out about this. We're going to basically send a spacecraft to capture some samples and bring them to Earth and analyze them. That's the only way, apparently. Okay, so we're gonna take some questions from the audience. I know we don't have much time. Let me see. I have some questions here. How long does it take Mimas to orbit Saturn, and as it is Saturn inner moon? Oh yeah, okay. So the period of rotation of Mimas, you can Google it very quickly if you don't know it by memory, but also in days. So is that a very close moon compared to the other moon? Is that close to the rings, close to Titan? Where is Mimas in this complicated system?
Yeah, it's somewhat close to the rings. It revolves. I can give you in numbers. I mean, if you are interested in kilometers. So the diameter of Saturn is typically 60,000 kilometers, and Mimas is at roughly 3 times the Saturn radii. So it's somewhat close, and it revolves around Saturn around a bit more than a day.
All right. Yeah. And you can see Mimas with a small telescope, right?
Yes, you probably can do that. Yeah. So I would say that the issue probably is the rings, the proximity of the rings. So, but yes, you should be able to get Mimas somewhat quickly. Somewhat early. It has been discovered it's quite some time. So, yeah, it's not the easiest one to catch, especially for astrometry from the ground, because generally you have the scattering of the rings. So you have kind of a halo coming from the rings. And Mimas is not that far away from the rings, but yes, it's not a difficult target.
So it can be lost in the glare of the rings if it's if the configuration is not good. All right. So Ralph Walter. So the moon is sloshing slightly, like rotating a pail of water back and forth by its handle. Oula. So it's basically he wants to Ralph, I think, wants a confirmation of the mechanism that you describe of what the moon is doing concretely. So it's liberating and it's moving on its orbit. What kind of, well, you explain what is the liberation. The motion on the orbit, maybe you can tell us, is that a motion, it's orbiting around Saturn, but what is moving exactly? Is the orbit itself? What is the motion we detected here, this 10 kilometer?
Yeah, so the orbital motion of Mimas is extremely complex because it's disturbed by many other moons, as you can guess. It's disturbed by the rings, it's disturbed by Saturn itself, which is not a homogeneous sphere. And so it's very complex. So you know generally that we used to say that planetary orbits are ellipses, Keplerian ellipses. Mm-hmm. Well, that's you are really in the simplest case. In the case of Mimas, not the case. So you can still say this is a rough elliptical orbit, but these ellipses will, of course, slightly change. We'll have some kind of small oscillations, but more interestingly, it will drift over time. And this drift is typically what we are looking for. So we wanted to look at a very high accuracy on the drift of the orbit over time. And if you have enough accuracy on that, you might be able to measure this extra drift coming from the feedback of the rotations, basically the presence of the ocean on the orbit.
All right. Can you tell us the technical term that you use for this motion of the orbit?
Periapsis drift.
Again, periapsis drift.
Periapsis drift.
It's the motion of the perihelion, basically, something like that. Okay, good. We have another questions from about the rings. I saw it and then it disappeared. Someone removed it? No, should be here. Okay. But you answer to this one. Does the mass of the Saturn rings have effects on Mimas oscillation? Do you take that into account? No?
Well, the mass of Saturn rings, generally, you can integrate them in the mass of Saturn itself. So the mass is fine. So what you might say is that at specific places in Saturn and rings, especially the Cassini division, I don't know if we're going to have time to discuss that, which is very super exciting topic. Then these ice particles that are a specific distance to the rings, to Saturn, they may have a significant influence on Mimas orbit. But then it's probably associated with tides, so it's probably not really to this periapsis drift we considered. Yeah, so that's a super cool topic.
Okay, we're gonna have another conversation on this, I'm assuming, in the future. Another question: does that Mimas have a big crater? Will sign of the ocean show up at the bottom of the crater? So, what the thickness of the crust? Just give us an idea, because I don't think we mentioned that.
Yeah, it's between 20 and 30 kilometers thick.
Okay. And the crater, go ahead.
Yeah, and it's actually there is a paper by Roden Walker at Boulder who basically showed that this kind of thickness is fine because this is the thickness you would expect to not see any activity at the surface of the icy crust, because it's thick enough so that at least in a short amount of time, I mean less than 25 million years, you don't see anything at the surface. It's also pretty clear that the Herschel crater arrived much before the ocean itself. So don't imagine
much
that
before.
Yeah, it arrived before, and the ocean arrived after that.
Okay. All right, cool.
If you do that the other way around, then you could be surprised for sure.
I was trying to find the depth of the Herschel crater. I can't find it. If you know it, let me know.
Sure. I would say a few kilometers, maybe
5 kilometers.
Or I had 4 in mind. Okay, it's 5.
Yeah,
okay.
5 kilometers. Okay. Do we know any detail from Cassini or from JWST? So am I translating this question? Is that so the study you did was from using Cassini observations? Are you expecting to get something better coming from JWST?
Well, it's the first time I didn't expect this question. I would say that the ocean is pretty young. The icy crust is pretty thick. So I probably do not expect to see something at the surface at the moment. So I probably would not expect something from JWST.
Okay. Thank you, Julia Braller, for the 100 star on Facebook. We appreciate. We have Dorian has an interesting long questions. Based on this discovery, will you be able to discover other bodies of water across other moons, asteroids? How many observations are necessary to perform this kind of analysis? Well, okay. So, do we know other moons with ocean underneath, first of all? And do you think you're going to be able to use the same technique from other moons around Saturn or other major planets?
All right. So yes, we already have. Mimas is the 5th moon to have a global ocean. So you have in mind probably Europa and Ganymede, the two big, some 2 Gallian satellites of Jupiter. And then you have Titan and Enceladus, 2 satellites of Saturn, and now we have Mimas, which is the most unlikely moon to our global ocean for sure compared to the other ones.
Okay.
We already have those ones. Now the technique we used, to be honest, we tested it. You know what? When you're trying to this kind of work, you also need to convince people that your method is working. So there is a bit of strategy, and with my colleagues Nicolas Rambaud, Nick Cooper, Xifeng Zhang, and we decided, well, we should test the method before. And we decided to test this study, this celestial mechanics thing for probing the interior of satellites on the inner moons of Saturn. So basically the small ones, Janus, Epimetheus, Prometheus, Pandora, and so on. And we did exactly the same thing. We looked at the periapsis drift, and we were able to infer the homogeneity of the satellites. So the idea was not to look for ocean because those are small bodies, but we're showing that by using this method, you can infer some interior properties. And once it works, then we apply that to Mimas. And we knew that for Mimas, it should work because this method requires the satellite to be close to Saturn, because the further away you are, the slower is the periapsis drift, and so the longer time you need to infer the signal you're looking at. So for Mimas, it's working well. For Enceladus, the signal is much, much smaller already. And if you go even further away, it's going to be super tiny. So you're going to need probably a space mission or something like that.
Okay. Well, I have a final question. I think I have plenty of final questions. So I need to think about the one that I really want to ask you. So you have made the discovery, published this in Nature. What's the next step? What's your next big project? I mean, there is so many moons in the solar system. So tell me, can you give us a hint of what you're working on at the moment?
You want to know, right? I don't know. Well, it's pretty clear that we don't want to wait the next space mission because it takes a lot of time. So if we can try to say something in between this next space mission, we'll do it. So I would love to know more precisely what is the age of the ocean and Mimas. And at the moment, we are saying it's below 25 million years and probably between 5 and 15 million years. So the uncertainty here in the age of the ocean is related to our uncertainty in the interior molding, especially of the silicate core. If we succeed in decreasing the uncertainty on the ocean age by just more precisely studying what kind of interactions the other moons created on Mimas to pump its eccentricity, how the Cassini division formed. Now that we have more information about Mimas, we may have a complete picture of what happened. And if we can do that by gravitation again, celestial mechanics, if we succeed in decreasing the uncertainty on the edge of the ocean, this means that we will be able to be more precise on the interior of Mimas. And in that case, we may be more precise, for instance, on the temperature of water at the seafloor. So is it 10 Celsius degrees? Is it 50 Celsius degrees, 60 Celsius degrees? This is probably the kind of thing you would like to know. And this kind of thing is feasible if they succeed in having full, complete picture of the dynamics in the recent past of Mimas.
No, we have one more minute. What is the next mission to Saturn? Do we have any in the pipe?
Well, we have one. It's called Dragonfly. So it's a fantastic mission. I love it. But it's going to study Titan. So it's not really, it will not look at Mimas and Enceladus, but basically it's a quadcopter that will go inside Saturn's thick atmosphere, and with autonomous navigation, you will basically go from place to place. I mean, I'm a great fan of this mission. I found it really fantastic. For me, it's a sci-fi mission that is going through, and I'm not part of the mission, by the way. So I'm not saying that for publicity. It's really, I love it.
Well, thank you very much, Valery, for your time. Thank you for telling us about the beauty of the ocean of Mimas. I'm disappointed there is no fish, no whales, no beaches, but not yet. We will see. But I learned a lot today. So thanks a lot for coming to talk to us that late and that quickly, in fact, shortly after the publication of your paper. I appreciate. Thank you to all our viewers, wherever you were watching us from. Remember, this is the SETI Live from the SETI Institute. We are a non-profit organization dedicated to the search and the search for life anywhere in our galaxy. And you can support us by simply sharing this video if you're watching us on YouTube, Twitch, or any of those platforms, commenting, tell us if you have any questions, something we did not address, something we would like Valery and I to answer to. We read your comments, we acknowledge them most of the time. So take the time if you have some very interesting comments about this research. You can also visit our website at SETI.org. Click on donate if you want to make a small donation to support our research, our outreach as well. And yeah, if you want to also receive news about the SETI Institute, we have a newsletter called Journée, and you can register to receive it on a weekly basis. So thanks again. And next week, we are going to talk with Teddy Tsanetos, who is involved in the Ingenuity mission. That's the drone that flew for a long period of time on the surface of Mars and just ended its life recently. So we are going to talk about this mission and what was learned with the Ingenuity first drone in the atmosphere of Mars. Thanks again, and see you next week. Thank you, Valery, again.
Thank you for bye-bye.